So, hitting just one last one of those preliminary topics before we start diving into our apothecary measurements and other things that'll prep us for our dosage calculation. And this is what I think is probably the most universal concept in math, the absolute most useful concept in math, and that is the concept of a ratio. A ratio is simply a comparison between two numbers. And I really should say between two or more numbers, because we can't have ratios that are, three-way, four-way ratios. So let's do a comparison here between this course and my course for Northwood Tech. I have, so do my high school students to my lack of better terminologies for the students here at the college. I currently have 9 students enrolled in the high school course, and I have 21 students in the college course. So I get that ratio just like that, 9 to 21. And that's one way to express it, is like that in that fractional form. There's a lot of advantages to having it in that form, because there are things that we will do with our ratio that are very similar to some of the things that we're used to doing with fractions. However, it's not a fraction, and there are some things we can't do with it. Another way we could express it is like this, with a colon, 9 to 21. Or even with the word 2 in there, 9 to 21. Come back to that wording there in just a second. A little bit of a caution is when we use that wording, there's slightly different wording that means slightly different things if we're going to express it that way. Now, what I said that we express it as a fraction, often we use it that way because there are things we do that we're used to doing with fractions. And one of the things we're used to doing with fractions is reducing them. Both 9 and 21 can be divided by 3. 9 divided by 3 is 3, and 21 divided by 3 is 7, giving us 3/7. Now, just like we had said in fractions, 3/7 is equivalent to 9/21, or they have the same value. The same here. It's technically 3 out of 7 is equivalent to 9 out of 21. They look different, but they're expressing the exact same relationship. Now, that doesn't mean we can't reduce it in our other forms. We absolutely can do that. It's just we're used to doing that reduction as a fraction. In this form here, we would have done the reduction just like that. 9 divided by 3 is 3. 21 divided by 3 is 7. And we've reduced it. It's the same amount of work. It's just as easy. It's just not a process that we're used to seeing or used to doing. Back to this term over here, 9 to 21. That word 2 implies these are from separate groups. Another way I could have written that is 9 out of 30. Now, those numbers look like they're different, but they are exactly the same relationship. That phrase out of implies that this 9 is part of a larger group of 30. Expressing a ratio like this is very important in the medical fields, because there are a lot of our medical ratios that are expressed like that. Instead of one part compared to another part that makes up the whole, we're comparing one part to the whole thing. One example we'll look at later today is dilutions. We'll spend a lot of time with dilutions in Unit 3. And of course, that could be reduced just like any other ratio, both 9 and 30 divided by 3. So that would be 3 out of 10. That same relationship. Let's take a look. I know you guys can't see my room here real well, but I have tables in my room. We could do a length, width, show. Tables are 72 inches long and 18 inches wide. Now length to width implies that the length is going to come first. I'll put the 72 inches first over the 18 inches. Again, I'm choosing to use that fraction form, but knowing it is a ratio. Now, just like we could in fractions, we can cancel out common items like the inches are gone. 72 and 18, I can start reducing that just like I would any fraction. Both divide by 2. 72 divided by 2 is 36. 18 divided by 2 is 9. And there I see that both of those can divide by 9, giving me 4 to 1. Here's where our ratios and our fractions have some differences. If this were simply a fraction, I would write that as simply the number 4. But it is not a fraction, it's a ratio. And remember, the ratio has to be the comparison between two or more numbers. If I just write it as a 4, that comparison is lost. So this is 4 to 1. We have to leave it like that. Now this is actually a special form of a ratio called a unit ratio. A unit ratio just means it is comparing something to the number 1. And that second number, to what we're comparing to, is the value of 1. Now coming up, we will have at least one example today where I'll show you an inverse unit ratio. In an inverse unit ratio, it's the first number that's a 1. We're comparing it to some other number. And we'll look at how those get reduced here as we go along. Now you'll notice in both of the examples we've done here, the units were the same. This was comparing inches to inches. Up here, it was students to students, or people to people, however you want to look at it. And that is one of the requirements of a ratio. Not only do we compare two or more numbers, but they must have the same units, have the same labels. Or in terms of what we talked about in the first couple weeks, they must have the same name. You might have something like 2 feet compared to 18 inches. That's not a ratio as it's written. Fortunately, we can change the 2 feet, 24 inches to 18 inches. And now it's a ratio, and now we can reduce it. Inches divide out, and both of those numbers, 24 and 18, can be divided by 6. 24 divided by 6 is 4, and 18 divided by 6 is 3. Now, once again, we have to remember this is a ratio and not a fraction. This cannot be turned into a mixed number. 1 1/3 would not be correct here. It's no longer a comparison between two numbers anymore. Must leave it as 4/3, 4 to 3. But what if we have two numbers that have different labels that we can't change? Let's say we're going to go on a trip and we drive 365 miles, 7 hours. Up above, I was able to change the feet into inches and turn it into a ratio. Here, I cannot do that. I can't change the miles into hours or the hours into miles. This is what we refer to as a rate. That is the first big difference between a rate and a ratio, is the ratio compares items with the same label or same name, and a rate compares items with different labels or different names. Because of that, notice all of our ratios up here had no units in them. They were unitless. Our rate will have units, has to have units to tell us what the items are that we're comparing. The second big difference is while a ratio we would leave as 4 to 3, it would just fine most of the time, a rate is almost always expressed as a unit rate. That means, of course, that second number has to be turned into a single unit. The way we do that is just look at the number of that second number. It's a 7. And we'll divide by it. 7 hours divided by 7 is 1 hour. Now, in fraction form here, it reminds us that we have to divide the other number by 7 as well. 365 miles divided by 7 is, what's that, 52.857 143 miles, approximately. Now, a couple of things there. First of all, I'd round this off. I'm not going out to 7 decimal places. Might round it off to 52.3 or 52.29. We'll go 52.3. 52.3. Actually, no, I divided that wrong. That would be 52.142853. So 52.1 is what that would round off to. And then we tend to hide the appearance of that fraction in the units. Instead of doing 52.1 miles over 1 hour, we just write it as miles per hour like this. Notice the fraction appearance is now hidden in the units. In fact, we even go further than that a lot of times, and we get rid of the units even more by just doing 52.1 mph, where the fractional appearance is gone altogether. Let's say that on that same trip, we got 24 mpg. We all know that mpg stands for miles per gallon. So that 24 mpg really means 24 miles per gallon, like that. If we see rates in either of those forms, both of those are abbreviations, by the way. If we see rates in either of those forms, what we really need to be thinking is over 1 gallon. Because that's the form we're going to need it in to do any calculation. Well, since we're on the topic of rates, let's explore some more rates. If you work to earn, let's go with $95, 5 hours. Your rate of earnings is simply $95 in 5 hours, like that. But remember, we like to have our rates as unit rates. So we'll convert that to a unit rate by dividing by the number, the numerical part of that second number, which is the 5. So $95 divided by 5 is $19. 5 hours divided by 5 is 1 hour. And of course, we generally convert that to an abbreviated form of $19 per hour, like that. If you're working in a production setting, you might produce 520 parts in 20 hours. The rate of production, 520 parts over 20 hours. And of course, to make that a unit rate, we divide by the number in the second number, the 20. 20 hours divided by 20, of course, is 1 hour. 520 parts divided by 20 gives us 26 parts. So giving us that rate of 26 per hour. Now, as you've seen in these examples here, when time is involved in a rate, it does tend to be the second number in the rate. It's not always. There are times where we might take 42 seconds, perform operations. And I'm not talking about surgical operations, I'm talking about just flipping switches or whatever the required operation is for what we're doing. That would give us a ratio of 42 seconds for 3 operations. And then that would be reduced, of course, dividing by the 3, get us 14 seconds per operation. Very important in management for productivity is stuff like that. You might look at seeing, 4 patients over 28 minutes. So you're working on 7 minutes per patient. Times contact times and required times to perform those job duties, job operations. We're going to look at a lot of rates that look like this. We might have 4,800 milligrams over 12 hours. So our rate of medication there, 4,800 milligrams over 12 hours. And I'm just going to jump to the reduced form there. I'm going to guess you guys can divide by 12. That's 400 milligrams per hour. For our ratios, ratios are all around us as well. In mechanics, we're going to pretend I can draw for a minute here. Yes, I'm very well aware of my drawings. Pretend those look like gears. When we look at gear ratios in mechanics, is the size of the driven gear compared to the size of the driving gear. Sounds very simple, but it's not as simple as it sounds. Because we're looking at gears, are we measuring to the outside of the teeth or the inside of the teeth? How are we measuring size? Well, fortunately, when it comes to gears, if two gears are meshing, the distance from one tooth to the next has to be exactly the same between the two gears. So to compare size, we can just count teeth. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 teeth there. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 teeth on that gear. But we still have a problem because we don't know which gear is the driven gear, which one's the driving gear. Well, again, pretend this looks like a shaft with a small electric motor on it. Now, that motor is turning the 14-tooth gear. If I separate those gears, the 10-tooth gear will stop turning. That is the driven gear. It's being driven by the other gear. So 10 teeth go with the driven gear. The 14 teeth go with the driving gear. And of course, both those divide by 2 to give us a 5 to 7 gear ratio. And in most situations, and this is a perfect one, that ratio describes several items. It describes the number of teeth between the gears, but it also describes the ratio of RPMs between the two gears, the two shafts that they're on, and the ratio of torques transferred from one to the other. You're looking at construction. They have roof pitch. Now, roof pitch should be distinguished from roof slope. What you're probably used to hearing for a roof is slope, 412 slope, 1212, 612, whatever, as the slope. A pitch, the height over the span. So let's say we have a span here of 40 feet, a height of 15 feet. That pitch, 50 feet. Notice again, the units cancel out, feet divide out, and both of those can be reduced by 5 to give me a 3/8 pitch, or a 3 to 8 pitch. In the medical fields, we use ratios to constitute our medications. So we might have a 3 to 8 ratio of, now the generic word we use in this course for medication is the word serum. Serum will describe any medication or any active ingredient. It might not necessarily be a medication. It might be a sterilizing agent like iodine or rubbing alcohol or something like that. 2, and then our diluent we had mentioned, we use the abbreviation NS. It can stand for neutral solution or normal saline. So our next step from these rates and ratios is to use them to figure out a larger relationship. So we have this 3:8 relationship between serum and saline. How much saline do we need to mix if the doctor's orders that our patient needs 84 milligrams of that serum, whatever that active ingredient is. So the 84 milligrams here goes with the 3 because that's the serum to saline. So we put 84 on top, and to find this missing number, just like we did with percents back in Unit 1, cross, multiply, and divide. 8 times 84 divided by 3. We get 224. So we would need 224 milligrams of normal saline or neutral solution to mix with that serum to create the desired concentration for that patient to meet the doctor's order. This proportion, setting up two ratios like that equal to each other, is a very powerful tool. We've used it before in our solving percents. Let's talk a little bit about how it works here. We looked at proportions strictly as being two equal fractions or two equal ratios and how to solve them. And generally, we were looking at just having one single missing number. You know, we had 5 to 8 equals x to 100. And in that case, we did that cross multiply. 5 times 100, 500. And then divided by the number diagonal with our missing number, divided by 8, giving us 62.5. 5 out of 100 is equivalent to 5 out of 8. However, this is actually part of a longer process. I'm going to write this as the ratio of A over B equals the ratio of solve this equation. Now remember, when we solve equations, I can perform any operation I want to as long as I do the exact same operation. Stop. I can add, subtract, multiply, divide. I could do powers and roots if I wanted to, and it would still keep the equation equal. But what I'm going to do here is I'm going to multiply both sides by b. On the left side, that would be a over b times b over 1, which would just cancel out the b's, leaving me with a on that left side. On the right side, I'd add c over d times b over 1. Well, that's just going to give me c times b, or cb, for d. Now I'm going to work from the other side. I'm going to get rid of that d on the right side by multiplying by d. So multiply the left side by d. Now again, on the right side, I have cb over d times d over 1. These are just going to cancel out, leaving me with cb on the right side. On the left side, a times d is just ad. If we look back to our original proportion here, we see that relationship AB is just this diagonal, AD is just that diagonal, and CB is just this diagonal, B times C. So the cross multiplying and dividing is just a shortcut that comes from our regular algebra of equations by doing the same thing to both sides. I show you this because sometimes we're going to run into proportions where we aren't just going to have a single item missing fitting in one spot of the proportion. We might have something like this. 5x over 19 equals 50 over 95. As we go to try to solve this, cross multiplying and dividing here would be tricky to do because it isn't just one piece of the proportion missing. The variable is embedded within one of the pieces. So we can do straight cross multiply. So we'll do 5x times 95. 5 times 95 is what? 475 x. Then going this way, 19 times 50 is, was it, I believe, 950. And then, as we saw up above, those cross products must be equal. AD times AD has to equal CB. So we know that 475x has to equal 950. And now from here we can solve by simply dividing by the 475. You get x equals 2. This one looks less difficult, but it's actually a little bit more complicated. And we might have 21 over x plus 3 over 12. Now you might be a little uncomfortable with that 63 over 12, but remember, these are ratios. We're not fractions. We don't have to worry about improper fractions or anything like that. So as we cross multiply, going in this direction, x plus 3 times 63, well, that's a distribution problem. I'll put the 63 first, times x plus 3. Going this way, we've got 21 times 12, which ends up being, what, 252. And there's our equation. 63 x plus 3 equals 252. And now we proceed to solve. We have to combine what we can here on the left side. We'll distribute the 63. 63 times x plus 3 is 63x plus 189. Next, we'll go ahead and subtract the 189. 63x equals 252 minus 189 is 63. Last step here is pretty simple. Divide by 63, get x equals 1. Well, it can get more complex yet. I think you guys look like you're catching this pretty quick. So let's take a little bit of a jump up in difficulty. Something like 3x plus 1 over 30 equals 2x minus 1, 15. The variable here appears more than once. So we'll go ahead and do our cross multiplying. Going this way, we have 30 times 2x minus 1. That's just 30 times x minus 1. Going this way, we'll have the 3x plus 1 times 15. Well, I'm going to put the 15 first. So 15 times 3x plus 1. And then I can write that as the equation. I'm going to write it down below since I don't have a lot of room over here. 30 times 2x minus 1 equals 15 times 3x plus 1. And now I have to do my steps here, combining on each side. On the left side, I have to multiply the 30. I'm going to distribute the 30. 30 times 2x minus 1, x minus 30, equals, nothing more to combine on the left side, so I go to the right side. I'll distribute the 15. 15 times 3x plus 1 is 45x plus 15. Now I've combined everything I can combine. I need to get the variable on one side. I'll subtract the 45x from both sides. 15x minus 30 equals 15. Now we're ready to solve. Add 30. X equals 45. And we'll divide by 15. X equals 3. Any questions there so far? So these proportions can be used a lot in the medical fields. For us, we're going to talk a lot in Unit 3 about something called a dilution. A dilution would be like a 1 in 6 dilution. There is 1 part serum or active ingredient in 6 parts of total solution. This is that out of or in instead of to that we talked about at the beginning. So in this case, we have to be able to look at that ratio and see the other ratios that exist within it. If there is 1 part serum out of 6 total parts, I can write a ratio of serum to neutral solution or normal saline. There is still 1 part serum. Now, if there were 6 total parts and 1 of those parts were serum, 6 minus 1 gives us 5 parts saline. Now, these ratios are not equivalent numerically. 1 to 6 and 1 to 5 are very different, or 1 in 6 and 1 to 5, I should say, are very different. But they do represent the exact same relationship, because this is representing one of the pieces, the serum, to the total. This is just representing the 2 parts to each other. And there is actually a third ratio we could milk out of that. We know there's 5 parts saline, 5 parts NS, 2, we'll have the 6 parts of total solution. So when we're given a ratio like this, where it is 1 in 6 or 1 out of 6, where we know that the second number is our total amount, and we have to know in a case like this that there's only 2 ingredients. There are actually 3 ratios that are being implied by that relationship. We'll break those down a lot in the beginning of Unit 3 when we do our dilution. The other thing our ratios and proportions can be used for, we can use them for measurement conversions. For example, we know that 1 meter equals 1,000 millimeters. We don't necessarily know that yet. I'm assuming you guys know that. We'll go over measurements here in a couple of classes. Any equivalency like that can be used as a ratio within a proportion. We know that 1 meter equals 1,000 millimeters. What about 4.3 meters? I want to know how many millimeters that is. Well, I can set up the other half of my portion here. This is meters here. Now, this is a rate, technically, not a ratio. This is meters here, so I'm going to have meters up here. That would be where the 4.3 meters go. Just like with our percents, I have to make sure I match things up. So what goes on top on one side matches up with what goes on top of the other. So this being millimeters means this will be millimeters. And here, since we are just simply missing this number here, we can go ahead and cross multiply and divide. 1,000 times 4.3 divided by 1 is 4,300. And we've done a measurement conversion using that proportion and those ratios. lot of other methods for measurement conversions, again, coming up in the next couple of classes. The proportion is probably one of the clunkier ones, but it's good to know because there are situations where that proportion is maybe a little bit more intuitive. For example, when a dosage is given as 0.5 milligrams per kilogram of body weight. That's a rate, but it's saying it's an equivalency of 2.5 milligrams for every 1 kilogram. And I can set that up in unit rate like that and use it in a proportion. If I have a patient weighs 42 kilograms, I can find the dosage by completing this proportion. Kilograms are on bottom here, so I'm going to put the 42 kilograms on bottom on the right side, and I can cross multiply and divide. 2.5 times 42 divided by 1. Gives us 105 milligrams. Now the units here do work out as well. So I'm going to go ahead and I'm going to write out this calculation the long way. This is 2.5 milligrams times 42 kilograms divided by 1 kilogram. And you'll notice here the kilograms cancel out. So the only unit that's left is the milligrams. So the units should always work out as well within our proportions for our calculation. So let's take a look at a simple mixture here. Let's say we want 3 parts iodine and 20 parts of sterile water, normal saline. I want to know how much iodine or say we're going to need 2,800 milliliters of solution. So we're mixing this 3 parts iodine into 20 parts of saline or sterile water for some sort of disinfecting bath of some sort. So we have our 3 to 20 is a ratio. Now there's no units there because this is comparing 3 parts to 20 parts. So the same label, same units, so this is a ratio. No units involved. But we do need to note 3 is describing the iodine, and the 20 is describing the neutral solution, the sterile water, or normal saline. Then on the right side, the 2,800 milliliters of solution milliliters goes with the normal saline on bottom, and we will cross multiply and divide. 3 times 2,800 divided by 20. That was going to give me 420. Check it. It's 420 milliliters. So we would put 420 milliliters of iodine into that mixture for that prescribed bath. Okay, so this is, like I said, one of our more universal concepts in that. That is the applications. That's how we're going to be using it in this course, is those rates and ratios and those proportions as I just showed you. But for those of you that go on, there are a lot of other applications of proportions outside of this. One of them, similar figures. All similar figures are is when we have two figures where one is just either an enlargement or a reduction of the other. Don't have to be in the same orientation. With triangles, it's enough to know that two of the three angles are the same. This single arc indicates that other single arc is the same angle. Same here. Double arc indicate that those are the same angle. If I label my sides here, 8 inches, 12 inches, and 9 inches. And then come over here, I label this side 15 inches, and I want to find those other sides. What I need to do is I need to link up the corresponding sides. Just like up here, I had to have iodine to iodine and saline to saline. Down here, I have to link up corresponding side to corresponding side. Well, the 12 inches over here is between the angle marked with a single arc and the one that's not marked. Over here, single arc and not marked. That would match up with the Y. 18 is between the two marked angles. Over here, X is between the two marked angles. And finally, 9 is between the double arc angle and the unmarked one. Over here, 15 is between the double arc and the unmarked angle. Those are our pairs of corresponding angles. Next, we need to select one pair that has both angles, or both sides listed with the length. Well, we have the 9 inches compared to the 15 inches. Now, we could reduce this. Inches cancel out, both divide by 3. Give us 9 divided by 3 is 3, 15 divided by 3, 5. Here's a 3 to 5 ratio of sides between these two similar figures. From there, if I want to find X, well, X is from the same figure as the 15, so it's going to go on bottom. X corresponds with the 18, so 18 goes on top, and we cross, multiply, and divide. So here, 5 times 18 divided by 3 gives us X is 30 inches. And we can do the same process to find Y. We still have that 3 to 5 relationship of sides. Y also comes from the same triangle as the 15, so since 15 was on bottom, we put Y on bottom. And again, we cross, multiply, and divide. Oops, I got to put the 12 up top here, sorry. 3 times Y and 5 times 12 has to be equal. 5 times 12 is 60 divided by 3 gives us 20 for Y. Okay, I think you guys have had enough for the day. So practice with ratios, rates, and proportions is page 73. And the odds. Don't forget, by the way, you should have your test 1 back. If you want to redo any of the problems you had incorrect, you are free to redo those and send them back to me to get half your points back. Need help with any of them, please feel free to ask. But you guys have a great day, and we'll hope to see you all on Friday.